Hey, how you guys doing today? Happy Tuesday. Hope you're doing well. We've got a couple things on tap today. I'm going to talk a little bit about the lab from yesterday, and then we'll jump into our next topic, linked lists. So it should be a lot of fun. Linked lists are really cool, but it's very conceptually different to what we've been doing so far today, or so far in the class. So it's a very different data structure, which is cool. And then that will take us through our midterm review and midterm the week. So we do have the wellness break coming up next Thursday, so we won't have class then. So we're going to do review next Tuesday. We'll do the midterm in lab or using the lab time to do the midterm, since there won't be any new content for us to talk about. And I'll just have that open throughout the day for you guys, but the idea is it'll have a time limit. So unlike the quizzes we've been doing where you have all week to go in, go out, start, whatever, stop, this will be once you hit start on it, you'll have about an hour 45 to hit finish or submit. I might bump it out to 2 hours, but again, I'll have a time limit specifically. So we can do some review. I'll give you last year's midterm for you guys to take a look at and see. And we can go from there. All right, so let me fire up PyCharm. Sorry, I should have opened that first. We'll take a look at the lab first. We were just using the circular queue, mostly just copying off of what was in the book there, and then trying to add that method of like getting the raw contents, just returning it as a string so we kind of visualize it ourselves. So the book had some good pictures of showing like, okay, this is what the status looks like. Here's the empty spots. Here's where things are. But I wanted you to be able to experiment and show that yourself, and then some more practice with the unit tests. Unit tests are always good. So let me see what we have here. So I got to start up a new project. Close this one down. This one is Lab 3. Okay. Here's our PyCharm window. And I'm sorry, my amazing mother-in-law had just stopped by like right as we were about to start. With a batch of punchkis from a local bakery. She decided to brave the snow today while she was out and brought some for us. So I had to go, of course, sample that. Make sure they were okay before we give them to the kids. Wouldn't want the kids to have disappointing punchkis. All right, so we got the lab project here. I'm just going to go copy paste if you don't mind, because you don't want to have to watch me type all that stuff. And the initial part, just getting that out of the book, was not super interesting, right? So, but the adding to it was more interesting than that. Circular, where was it here? Q. Sorry, gotta find it here. Why? It's taking me forever, sorry. Nope. Do we not have it? Maybe I don't have it to copy there. Huh. It's weird. I thought I had that one there. Well, that's okay. That's okay. We can go get it from over here. Not a big deal. Oh, that's going to be ugly to copy paste. Shoot. That's unfortunate. I wonder, I might have it here. Let me just do some more searching here. Aha. I think I've got it. There we go. I've got one here. That'll work. This is just a little bit different. Let me slide it back down to 10. Just a little bit different syntax than what the book was going. I was tracking the back and the front. So that was all. Let's see. Yeah, and I would just reset. So I wouldn't even bother doing the modulus. I would just reset back to 0 every time we took an item, or every time we queued an item. So it's essentially the same thing. And then we were adding the was it get raw contents? And essentially that would just return a string version of self data. And that's about all we needed to do there, because we've got data as the list here. Then we could take a look and play with it and see. So if we're to make a new circular queue, queue is a circular queue, and then we'll add a bunch of things. I don't know, so for n number in range, let's add 5 items. Take our queue.enqueue, we'll enqueue the number, and then let's print the queue. Get raw contents. So you should be able to see it's going to put in a 0, 1, 2, 3, 4, 5, 4, and then let's dequeue a couple. So we'll take our queue, dequeue, I don't know, let's like maybe dequeue 3 of them. Let's print it again. And let's enqueue a couple more. This time let's start at 5 and go through 9 maybe. Queue enqueue, and we'll print that. And then maybe dequeue 2 more and print it. Let's enqueue a couple more numbers there then. Let's start at 9 and go through 12 or so, and then we'll print. Let's see what we get. Again, just trying to experiment, look at, visualize what's happening inside this circular queue. Okay. We're looking good so far. So we have the first 5, and then we get a bunch of nuns, and then we dequeue some, and we see we replace them with nuns. We add a couple more, still have some nuns on either side. Dequeue a couple more, still have some nuns. Add a couple more. Once we reach the end, we just wrap around to the front here. Let me add a couple more here then. 13, and let's go up to, say, 18. And once we fill it completely, right, we're going to add 12, we're going to add 13, we're going to add 14. Once we fill it, we're going to have to resize ourselves, and everything then will shift back down. We'll add a couple more, and then we'll print. So this we expect to be in order here then, once this one's done. Right, because we put in the 12, the 13, the 14, we ran out of room, we had to resize, so everything gets shifted back to the front here. And then we were able to add a couple more to the back and just keep on going. So just looking at this circle here and trying to visualize how it's going, right? And get that idea of, okay, so if I see as we have empty spaces, we fill them up. Okay? All right. This will make it sense for the lab, and then just unit tests, like, hey, here's the string I'd expect to get. I think I gave you a couple examples of, this is what that string might look like. Okay. All right. Nobody has concerns in chat. That's good. That's good. So that was the lab, just experimenting, visualizing this one. I think the stack is a little bit easier to visualize because you kind of understand, you stack things up, take things off the top, put it on the top, and that's all it is. The circular queue is a little bit trickier. Okay. So I'll push that one out to GitHub in a second, and let's start a new project. This is linked lists. And remember, when we talked about performance, on average, right? Again, mostly we care about average performance. We don't care too much about best or worst case. I mean, worst case is important, but we're going to mostly ignore it here. Okay. There we go. And so for adding something to a queue, adding to the front, with that circular queue, we had constant time. Because on average, we don't need to resize. And if we do, we kind of amortize that across. We get constant. To dequeue something, we know right where to take it from. So it's constant time. We just replace it with a none. And we're in pretty good shape. And we're not going to be expanding our use of memory the more items we add. Remember, the problem with that dumb queue was we just kept on adding to the back and taking from the front, and we never were able to resize ourselves. So if we get too big, too small, right, the Python list is going to take care of that for us and shrink itself if we need to free up some of that memory. So we're not holding on to it forever. So the performance is really good, but all we get is taking from the front, adding to the back. Right? But we were able to solve that other problem. So our stacks and queues are really fast data structures. Right? They're really quick ways to get at these items here. But we have limited access to them. So what we're going to do is we're going to look at a linked list instead of an array list. So Previously, we had done that array list where we had to keep these items in contiguous space in memory. And the problem with the array list is, remember, inserting into the middle means I have to shift n items, or taking something out of the middle means I have to shift n items. So there's a lot of shifting happening here with this is the array list, right? So appending was fast, right? Append was O of 1. That was quick. Pop at the end, right, was O of 1. That was fast to take off from the end. To get by an index was O of 1. That's really good. If you know what the index is, we can get it like that, right? Because we'll just figure out where it is in memory, and then we've got it. What happened to my O there? There it is. That's weird. Okay, so appending, popping, getting, those are all really quick. And again, on average, these are average times, right? Average. Right? With a linked list, let's talk about what is slow. So insert at, k index is really n minus k. Right? However many items I had, minus how many I had to shift. So if your k is at the very end, you only have to shift like 2 or 3 things. Right? And then remove or pop. I guess we should just call it pop, right? So pop of k, right, is n minus k. Again, so the more items I have, the longer that's going to take to do that shifting, to pop or remove. With a linked list, we can get better performance in some of these, but we're going to lose performance in other cases. And that's where it gets interesting, and that's why we study these things. Am I with you guys still so far? All right, looks like I'm streaming. I think I lost it on my preview playback. Sometimes it just screws up. All right, let's pull this up here. So far, we're going to give you access to the front when we do a linked list. So the idea with a linked list is we are tracking links. So I have a node. The node has 2 things. The node has data, and it has the next node. And I can create nodes as many times as I want anywhere in memory. Uh-oh. I gotta refresh. I might lose chat here in a second. Let's see. It still says we're stable. That's a good sign. Let's give it a minute to refresh. Been having Comcast issues today, which is unfortunate. Let's see. Give that a minute to refresh. It's still refreshing. Thinking hard about it. Maybe. I think we're good. I don't know why it just won't show me the page here. All right, second refresh seems to be working better. All right, I'm back in chat. Hey, folks. All right, so anyway, we use these nodes here, and the next is really, it's a pointer to where the next node is, right, with data and next. The cool thing with this is these nodes can be anywhere in memory. Doesn't matter where they are. We just keep on pointing. When we get to the end, next is none. There is no next, is how we indicate that. So linked lists usually have a front, and they have a back, or tail, depending on what you want to call it. Sometimes tail, sometimes back. And they're fun to interact with. So if we want to build a class for linked list, or a class, this is a singly linked list. That'll mean more things later. Don't worry about it too much right now. Define init. And we'll have self.front is none, and self.back, or we can go with tail, doesn't matter. Front and tail I will go back. Front and back is none. I don't have any front, I don't have any back. Self dot number of items. Of items is 0. Head and tail. Yeah, we could use head and tail, sure. Head and tail. Yeah, the head of the list, the tail of the list. Sure. Imagine, kind of think of it like a snake then, right? With a head and a tail. I mean, it doesn't matter. We can call them whatever we want. Front. Back. Yeah. Okay, number of items. Cool. And we're going to have a couple methods, but we also need a way to have these nodes. So no one needs to care about nodes. So nodes is actually going to be a private inner class, which is crazy. We're going to create a class called node. And we define an init here. So init wants the data, right? And a next, we're going to default next to be none unless you tell me otherwise. So self.data is the data, and self.next is the next. And that's all node is. That's the entire node class. Right? Because we can just get at these things. We didn't have any methods. We didn't have any special access. They're just public here, but they're internal to singly linked list. So it's fine because we want full access to them. We're not really protecting anything here with these nodes. We're just keeping them. It's a helper class to the singly linked list. Okay, and then we're going to have a define. This is an add to front, given some data. So we'll add data to the front of the list. Now this works out really easy, right? We can take the data and make a new node out of it, right? So I'm going to make a new node. So this is my new node is a node given the data. And what comes after something that we're adding to the front? Well, whatever the head currently is. Self.node? Is that it? Yeah, self.node. Okay. We make a new node. So what's going to come after, right? If I want to add something to the front, let me scroll. Nope, that's the wrong button here. So if I had something here, right, with say E in it, and it didn't have an extra, if this was our head. To add to the front, I'm going to say, hey, here's a new node. Let's add A to a node. Its next is this one. Right? We can add the item. Sure. Now head is here. Doesn't point over here. Right? And then items plus plus. Or items plus equals 1. Right? Add an item. Sorry, my chicken scratch is bad. So adding to the front's really easy. So, but then we need to track that now self head is the new node. Right? We're going to reset, say, okay, head, you're now the new node. Great, done. Oh, and number of items plus less. Self dot number of items plus equals 1. Now the problem that we have here is this was all well and good, but we also had, so if we were a linked list here with just one node, and I had E, and it didn't have a next, its head, right? It's also the tail. Right? Because if you only have one item, you're the front and the back. You're just one item. You're one thing. So sure, I can add a new item here. We can add A as a new node. Its next points to the current head. And then I say, okay, head, you're no longer here. You point here. This works great. Tail's no problem. But we also have the case, though, if we didn't have head was none and tail was none, right? Then when I add the node, sure, I'm going to say, okay, here's an A. Right, let's add an A. Its next is the current head. It's none. So it has no next. And then head points to here. I also need to update tail. Because now I would have left off tail. And I would be in trouble here trying to get at items at the back of my linked list. So I need to check if it's now the only thing, I need to update tail as well. So we have to add a little bit of special handling here. So we can do that. So we can say if, and we can do a couple things. We can check if the next is none. We can check if the number of items is 1. I mean, whatever we want to check. I like checking for next. So let's do that. So we're going to say if self.head dot next is none. Self dot tail is self dot head. I could also use new node. Either way is fine. We'll set it to new node. Why not? New node. Right? Oops, we don't need those parentheses. My mistake. Okay, so we'll add the new node, whatever data we were given. Its next is the head node, whether or not it exists. Right? It might be none, it might be a node there. Then we're going to repoint head to the new node. We're going to say, okay, we've added an item. And then if we didn't have a head currently, right? If the thing that comes after us is none, it means because we're the only item here, we're also now the tail. Right? We're adding in the very first item, we're the head and the tail. Okay? We can do a add to back, given some data. Works almost the same way here, but not quite. So it will have none as its next, because if we're at the end, remember the end of the linked list says that you don't point to anything else, which is fine. And then we're going to take our self tail, we're going to repoint it, tail next, to the new node. Right, so now tail is the new node, sure. And then self number of items plus 1. Right, so say we had a list here, and we had A, where it's the head and the tail. We're going to add to the back here. So let's add, say, I don't know, a H. Its next is none, because it's going to go to the end. And then we're going to take our current tail and say, oh, you're no longer a none. You don't point to nothing now. You now point here. Then we need to move tail, right? So now tail no longer points to this one. No longer the tail. Tail is now the new thing I just added. We're going to update tail. Self.tail is equal to the new node. Okay, so make a new node. It doesn't have anything after it. It's the end. The previous ends now has something that comes after it, and we're the new end. Give me just a second here, sorry. Hey, sorry about that, folks. I had to take a call from the doctor's office. All right, so we're talking about our linked list, right? Adding to the back. Now, this is going to work great, but we also now have a problem if we're empty, right? If head is none and tail is none, we have a problem because I can't go in and say, oh, tail, you don't have a next because tail doesn't exist. So we need to be careful here. We need to be more careful here than previously. So the new node is fine. We're going to say if self tail is none. So if we don't have a tail, then we don't have to do this, right? Because all this happens separately. So if tail is none, we just do this step, right? Otherwise, we're doing this step. So really, we can check. We can say if tail is not none. No, I'm sorry, because we have to do that. So we're going to say if tail is none, then tail is the new node. If tail is not none, then I can set the current tails next to the new node. Right? So the two different cases here. So if tail is none, whoa, there goes the pen. We're going to say, all right, we are now the tail, and our next is none. And if the tail was none, that also means the head was none. So we'd have to set head to the new node as well. If head and tail weren't none, or if tail wasn't none, then I can say, hey, tail's next. The previous last thing is now the new last thing. Okay, so if it was none, we're going to now say, okay, tail, you're on the new node here with the letter F or something. And then we're also going to set head to that node. So we have some special cases to consider when we're working on adding to the front, adding to the back. Okay, and again, always adding our number of items plus 1. Maybe we'll do that as the last thing over here. I don't know, just to make it consistent looking, right? Okay, that's what it wants. So we can add to the front, we can add to the back for our linked list. It's going to take some practice. These are interesting to visualize here. So we can add to the front, we can add to the back. Now we can remove from the front really quickly. Right, so removing from the front, this is define remove front. We're going to have the item, or the data is my self front. Remember, because front is a node, it has the data. So that's the data we're going to return, right? Then we need to move front. So if we had a list here, I want to zoom in, sorry. So say we had a list like A and H. If we wanted to move front, we're going to take we're going to take our A, put it over here. We're going to none that out, right? So we don't have any references to it. And then we're going to move front or head to whatever my next used to be. Okay, so we got the data. We're going to take now self front data, set it to none. This is cleaning up for garbage collection. Garbage collection, right? Making sure it can get cleaned up here. Then we're going to set front to fronts next. So self.front is equal to self.fronts next, whatever it used to point at. And this might be none. Right? If we only had one item, it's none. If we have multiple items, it will be the next thing in the list. Why is it not like that? Instance attribute defined. Oh, that's fine. Oh, I'm sorry, it's head. Sorry, head. I'm getting myself all confused here. Head and tail. Okay, not front. Head and tail. Like that. Next. Okay. Trying to make it be happy with all those lines here. All right, so the data then we're going to none out to clean up for garbage collection. We've got the data to return. We're going to repoint head. Now the problem we might have here, right, is if we had only one item. If we have only one item, sure, head will now point to none. Head will be nothing, but tail needs to get cleaned up then. So we're going to have to check. So we can say if self.head is none, self.tail is none, equals none, right? Clean up the tail, And then once we've removed an item, you need to take one away from our count. -1. We should probably also check, right? So if self.number of items is 0, raise a, I don't know, some sort of value error. List is empty. Sure. Right. See, we can't do it because we're empty. Now, what's cool about this, the performance of these, right? If we think about how fast it is, no matter how many end items we have, there is never resizing. Right? There's never that doubling process that has to happen. So our add, I cannot type, I'm sorry, folks. This isn't typing. This is writing. Add front is always O of 1. Best case, worst case, average case. And again, usually we only care about average case, but it will never be slow. Add to front. Remove front. Same thing, O of 1. Always constant. And add back. Still O of 1. So the performance we get with a linked list is really, really fast for these ones. And again, this is still a little bit limited in terms of what we're doing here. Right? But what we have now, just this with this simple data structure, is we can use the linked list to build stacks and queues. This is a linked list stack. Define a init. We probably also need a size, right? We should add a length for this. So define length, return self.number of items. Line 32. 30. I just changed it here, didn't I? Tail, head, tail and head, head and tail. Oh, yep, self-print. Yep. Thank you. Head. I was just changing the line numbers on you. That's my mistake. Head. Thank you. Yep. Good catch. Hey, some 5 bonus points for you, Grenjith. Unfortunately, bonus points aren't actually worth anything. They're just satisfaction points. How about that? you get satisfaction points? All right, if we ever come back on campus, I'll owe you a Punchki. How about that? All right. So if we are pretending to be a stack here, we can have our internal storage here then. So self.data. Data is a linked list, singly linked list. We can define our length. We're going to return length of self.data. Right? And then we're going to have a, oh, sorry, another call from the office here. Give me 1 second, sorry, folks. All right, we're back. Sorry about that. Trying to, it's some med changes that are, it's a mess. Okay. So our linked list stack then, right? We could pop, or we could push, and you would push an item, right? Push an item. We're going to take our self data, and we want to add to front. add to front, given the item. And then define peak, right, was what's at the front. We're going to return self.data. And do we have a way of getting at that? Nope, we didn't. We could add, we could remove. So maybe we needed a way to peek at the front or something. Or just define front. Why not? Self.head.data. We probably also want to check, right? Make sure that we're not empty. I feel bad copy pasting that, but that's okay. Okay, so we can get the front. Dot front and pop. Return self.data dot remove from front. Remove front. Okay, so we push, add it to the front. We can peek at the front. We can pop, remove from the front. So remember, with a stack, it's first in, last out. So as we keep putting things in, we're just going to keep pushing them farther and farther and farther back. So we never deal with the tail. It's fine. We don't need to. It's not a big deal. Okay, we can always get the thing off the front. So in terms of operational speed, right? Constant time, constant time, constant time. There's never any resizing, like when we had that array list. Remember when we were using the internal list storage for a stack, on average, yeah, it was constant, but we did eventually have to do resizing as we got bigger and bigger and bigger. With our linked list, we never have to do that. So we gained some performance here at the cost of memory. So the sad part about linked lists is node takes up memory. So we're using more memory addresses than an array-based list, right? The array-based list just takes up, the 16 spots for memory or whatever it happens to be, and they point to all the things. With our linked list, we have nodes, and then we have other values. Let's see. Oh my goodness. Today is a crazy day. Yep. Oh my goodness. Now it's piano lesson time. Ay, ay, ay. Okay, give me another minute. I'm sorry, folks. This is usually we're more set up than this. It's been a rough day. It's been a rough day. We'll be right back. Put on some more music. Alrighty. Oof. Is it Friday yet? Are we there? We getting there yet? All right, so our stack here, the linked list, super performant. Again, it takes up a little bit of memory, but again, it's not too big of a deal. This actually works out well because we don't need to double our size with the array lists. Remember, every node takes up a space in memory, and then it's tracking the data, which is another referencing somewhere in memory, and then the next pointer is another address in memory. So using a little bit more, but it's okay. We're not too concerned. We're going to write a class for our linked list queue here. Now we don't have to worry about any of that circular nonsense, right? The init here, we just make another linked list. And again, length is good. And we do enqueue, dequeue, and front. So this is front. And then we can enqueue and dequeue. So we enqueue some data. So when we're going in a queue, remember it's first in, last out. So we're just going to take our self data and we're going to add to back the data. And to dequeue, we're just going to return self.data, remove from the front. So we take from the front, we add to the back, and new. Boom, now we're done. Now we're a queue using a linked list. So using linked list is really nice and easy for stacks and queues, right? Not too big of a deal here. That makes sense? Queue, yep, we got those. Awesome. How's it feel so far? So again, drawing out pictures for linked lists is super helpful. Why can't I get the video preview to work? It's just failing me. Let me just try and get chat on my phone here. I'll just close that because it is not cooperating. Let's go one of these buttons here, right? Come on, where'd it go? Where'd you go? There it is. Can't find Twitch. All right, cool. I got chat on my phone here now. I'll just close that preview because it's not working. All right, just make sure our connection's okay. Well, how's everyone feeling with the single linked lists? Cool. All right, awesome. So the next topic with linked lists is circular, but it's silly to do circular without doubly linked. So I combine these sections usually. We're going to talk about doubly linked circular lists. And it takes a little bit of thinking about how this all works exactly. And there's a little bit of trouble in there as well. And then the book goes into all sorts of fun things using base classes and wrapper classes, and that's a little bit more complex. I think we don't have quite enough time to get into that right now, so we might save that one for Thursday. But we also have, what do we have on Thursday? I think we had, do you have the project due, or is that next week? I have to check Canvas because I can never remember, I'm sorry. And I think I owe you okay, of course it's not loading. The first project is, I need to get that graded for you guys. Come on. Okay, I can't hit Canvas. Nothing. Come on. Find me Canvas. We were just there, computer. Come on. Why? Why is it not cooperating? There we go. Awesome. Yeah, so I owe you grading for project 1. And, oh, I never talked about the next project. That's right, so we are running behind on that one. I'm sorry. So we'll talk about the next project. I think we can do that. Yeah, we can do that. Let's do our next project here. We'll do that, and then we'll come up with more of the linked list stuff after, because this project is going to be based on stacks and queues. It's project 2, stacks and queues. So let's see, what was our schedule? We've got this week, we've got the midterm review, and then are we off on break? So when should this one be due? 16th, 23rd, because we're off that next week, right? Let me put it as the 9th for now. Maybe that'll change at 3:30. So I'll double check the schedule here. And this one's going to be worth 15 points. The backtracking is worth 10. This one will be worth a little bit more. All right. Work with the canvas. There it goes. All right, awesome. Let's see. I'll double check my home module. I don't know why this is loading so slow. I think Comcast hates me today. Maybe. Come on. Is it loading? Yeah, okay. Finally we're loading here. This page is just like locked. Nope. Online. URL. Awesome. And I'm sorry, I'm just trying to pull this up over here. Why do I have nothing here? Man, nothing is loading. I think the stream is still steady though, right? Like I'm not losing bitrate or anything. I just can't load pages. It's crazy. Yeah, nothing. Okay, I think I'm just locked up. I'll post the project and then I'll be hanging out after. If you have questions, it's relatively straightforward. We're building a little project using stacks and queues. I'll post it and I'll talk more about it on Thursday, assuming we can get things working again here. Yeah, just nothing's loading for me here. So why don't we call it a day? Go out and enjoy the snow. Hope you guys are keeping safe. And we'll talk more on Thursday then, okay, folks? All right, you take care.